The next speaker is Krishnaswami
Alladi. Thank you, Mel, for organizing this conference continuously for so many years and for inviting me. It's been quite a while since I spoke at this conference. I'm glad to be back. Carl Pomerantz mentioned a 1979 conference in Carbondale, Illinois. That was when I first met Mel Nathanson, and he invited me to give a talk there, but I spoke on irrationality inspired by some work of Aperi. But that was actually an important conference because I think that was the conference where Dorian Goldfeld announced his conjecture on elliptic curves, and it's published in the proceedings of the Carbondale conference that you edited. So your organization and editing work go back several decades. Thank you for your service. All right, so I'm going to talk about, actually start with work that goes back to my PhD thesis, but very recent developments with my two PhD students, Jason Johnson and Shravan Sengupta. So the talk will be mostly about this recent work, but I'll give you this background. All right, so that's sort of a general overview.
I'm sorry, we cannot see the slides.
He cannot see the slides. Can someone help? Can you see the slides now?
Yes, thank you.
Yes.
All right, good. Okay, thanks. So anyway, so this is sort of an overview of the talk, and I'll try to cover as much ground as possible. So let me begin with the background. So as I said, this goes back, I'll give something about my work of 1977. So there are these two famous results of Edmund Landau, that the sum of the Mobius function up to x, which we denote by m of x, being little o of x, and infinite series, n from 1 to infinity, mu of n over n being equal to 0, these are both elementarily equivalent to the prime number theorem in its simple form, pi of x asymptotic to x over log x. And of course, if you use, let's say, zero-free regions of the Riemann-Zeta function and improve the prime number theorem with strong form and error terms and so on, corresponding results hold for bounds for m of x, as well as size for the truncation of the series mu of n over n at the point n less than or equal to x. Okay, so corresponding results hold. Okay, so in 1970, the paper was published in 77, but actually I observed this in 76. I noticed a very interesting duality connecting the Mobius function with the smallest and largest prime factors of the integers. So you take any function f defined on the primes, and then you sum mu of d, f of the smallest prime factor of d, over divisors bigger than 1, because we need prime factors. And then you end up with minus f of the largest prime factor of n. And the process is reversible. So if you do mu d, f of the largest prime factor of d, you end up with minus f of the smallest prime factor of n. So when I found this identity, it was clear to me it has to have some really striking consequences, because it is so simple and nice. The statement that summation mu d dividing n being 0 has striking consequences. So this should have some interesting consequences. So what would be a good example of a consequence of this? So here is an interesting theorem. If you choose any bounded function on the primes, if that function has an average value on the largest prime factor, that is summation f of p of n less than or equal to x multiplied by 1 over x, if you take the limit as x goes to infinity, and if this has an average value, so this has a value c, then the series mu of n, f of the smallest prime factor of n divided by n from 2 to infinity goes to minus c, and vice versa. So the convergence of the Mobius series is related to the existence of the average of this function on the largest prime factor. All right, so this is a surprising generalization of Landau's theorem, because we normally state Landau's theorem as summation n from 1 to infinity equal to 0. So let's throw off the first term, mu of 1 over 1. And so we rewrite Landau's theorem as summation n from 2 to infinity equal to minus 1. Now go back to my statement. Just choose f to be 1 on all the primes. Then clearly the average c is equal to 1. And therefore the Mobius series will be equal to minus 1. So this is a surprising generalization of Landau's theorem. So Landau's theorem is the case where f is identically 1 on the primes. Okay. But we want something which is a little bit more striking. So now what we do is, let's say I choose f to be the characteristic function of primes in an arithmetic progression L mod k. The prime number theorem says that the primes are uniformly distributed in the various residue classes, reduced residue classes mod k. So you utilize that result, and now you prove that the largest prime factor, if you write the sequence of largest prime factor, that is a sequence of prime numbers with repetition, that repetition does not destroy the uniform distribution modulo k. So you prove that the sequence of largest prime factors is uniformly distributed in the reduced residue classes modulo k, which means if I choose f to be the characteristic function of primes in the residue class L mod k, then that c that you have there will be equal to 1 over phi of k, which means this Mobius sum will be minus 1 over phi of k. Now this is really quite striking and surprising, because what is it that we have done here? We have taken the convergent Mobius series mu of n over n from 2 to infinity equal to minus 1, and we have sliced it into phi of k subseries, and all the values are the same. So I challenge, take a convergent series like log 2, slice it into 10 subseries, all having value log 2 divided by 10. So maybe I should offer a little prize money for it, $10 or whatever. But the thing is, it's not easy. You can't do it. Divergent series you can. You can truncate a divergent series at x, and you can take subseries, each of which is asymptotically, 3 subseries, each asymptotically equal to 1/3. Because in a divergent series, the main contribution comes towards infinity. In a convergent series, it's so sensitive to the initial values, you don't know how to slice this. So the nice thing about this result is you can slice this for every k, and the slicing is done using the smallest prime factor. So that was what motivated me to publish this paper on duality between prime factors and the prime number theorem for arithmetic progression. So this is related to the prime number theorem for arithmetic progressions. Now, what happened was, so this was 77. Now, after the Ramanujan centennial, I moved to the theory of partitions in Q hypergeometric series, and for 25 years I was not working on analytic number theory, so I never attended some of these conferences. Meanwhile, in 2017, Ken Ono invited me to give a talk to his REU group. And he said, you should talk about, so I spoke about this Mobius series, thinking it will be of great interest to these students. But he actually turned towards his PhD student, Madeline Dawsey, and said, rewrite Alladi's theorem as minus of the Mobius series over small prime factors L mod k equal to 1 over phi of k, interpret it as a density result, and now generalize this to algebraic number fields using the Shebatarov density theorem. So he actually said this at the conclusion of my talk. And then within a few months, Darcy published this paper generalizing my results to Galois extensions of Q and using Shebatarov density theorem. And then a whole bunch of other results came, one of which replaced the Mobius function with the Ramanujan sum And then they had Liouville and various things. So there was a whole group set of papers that came through. And actually, Ono himself wrote a paper on Q analogs of this result. Okay, so I was thinking maybe I should come back to this area. At that time, Jason Johnson came and he wanted a PhD thesis. So this is what happened. Actually, back in that 1977 paper, I had higher order dualities. So let pk of n, little pk and capital Pk denote the smallest and kth smallest and kth largest prime factors of n. And obviously, if a number has fewer than k prime factors, you just set these values to be 0 or 1. Now, if you look at the sum mu d, f of the kth largest prime factor of d dividing n bigger than 1, I put a star there because the star means summation over numbers with number of prime factors less than k means the sum is 0. This turns out to be related to f of the, not the kth smallest, the smallest prime factor of n, but multiplied by omega n minus 1, choose k minus 1. Okay, and of course you can reverse this. You can interchange the roles of the smallest and largest, and so you have this duality. But I never investigated consequences of this duality, and neither did this group of young mathematicians trained by Ono and others. So they all looked at the original duality. So I told my student, maybe it's worthwhile going back to this and discussing, let's say, k equal to 2. So k equal to 2 means this duality is this equation 13. You have summation mu d omega d minus 1 times f of the smallest prime factor of d is f of the second smallest prime factor of n. So I said, let's first start with this before we go to general k. Now, this is a little bit more complicated than the earlier one because we are dealing with a multiplicative function and an additive function, omega. And you'll see that the asymptotics is quite different. But anyway, the first observation is that analogous to Landau's result, we can now prove that summation mu of n omega n divided by n is 0. And if you now write this as 2 to infinity, you'll still get 0 because little omega 1 is 0. So there is no change in that. Okay. But now, interestingly, this series can also be sliced into phi of k subseries, and all the values are 0. So that means, once again, you're doing a slicing in with all values being equal. Of course, you can also get minus 1 over phi of k, or 1 over phi of k in this case. If you replace omega n by omega n minus 1, then, of course, that's how the original identity is. You'll get 1 over phi of k. So we prove all this quantitatively and first announced this in 2024. And of course, the paper has now appeared in a journal issue for the 85th birthday of George Andrews and Bruce Barth. Now, I'll tell you about Tenenbaum. I wrote to Tenenbaum about this, and he wrote back with some specific results. I'll get to that later. So the main thing I wanted to say, the difference between these two problems is that if you look at the psi function, psi of xy, the number of integers up to x, all of whose prime factors are less than or equal to y, and let's say alpha is log x over log y, this function decays quite rapidly as y drops away from x and comes down. So the decay is like x alpha over 2. In contrast, the number of integers up to x for which the second largest prime factor is less than y, even though it could be little of x, is not decaying as fast, because obviously the smallest value of this will be psi of 2 of x2, where the smallest prime factor is exactly 2. But if you look at numbers of the form 2p, 2 times an odd prime, those numbers will have smallest prime factor 2, and the number of such numbers is x over log x. So this will never be smaller than of the order of magnitude x over log x. So it's not going to fall as rapidly as x e to the minus alpha over 2. So there is a marked difference between psi of xy and psi 2 of xy. So the asymptotics is somewhat harder here. All right, the second thing I wanted to say is this function m of x, which is the sum of the Mobius function up to x, that, if you use the strong form of the prime number theorem with the de la Vallée-Poisson error, is of the order of magnitude less than x e to the minus root log x. But we can actually show that this m omega of x, which is summation mu of n omega n, is asymptotic to x over log squared x. So that makes the problem a bit more difficult. But also this tells you something else which is different from this, which is in terms of integrals, which I'll come to in a moment. So here is how you attack this particular situation. Write omega n as summation chi p of d, where chi p is the characteristic function of the prime powers. Then you use Mobius inversion, and then the fact that capital omega and little omega are the same on the square free tells you that mu d little omega d is the negative of the characteristic function of the prime powers. So m omega x can be now written in terms of this characteristic function, and that using Mobius inversion. And now you can use the hyperbola method and elementarily derive, but using the strong form of the prime number theorem. Yes?
P1 being less than y versus P2 being less than y?
Yeah, that's psi 2.
Yeah, so your concern is that essentially the second prime factor and thereafter all like become degenerate at 2, and then you just account for prime. But is what you're saying that if you maybe weight by having many prime factors, so that would kind of get rid of the issue. So like
no, but this is the smallest possible value of psi 2 is that x2 is at least as big as x over log x.
I understand. The point is, if you want to kind of compensate for that fact and maybe weight by numbers that have more than 2 prime factors, maybe is this what this kind of omega weighting is doing?
It's not quite the same. I mean, there is a cancellation coming because of the Mobius function due to my duality. Okay, so that has to be taken into account. See, the Mobius function is itself also introducing a cancellation. Okay, so we're going to get a convolution of this chi p and that to first get this idea, but then we're going to use the second largest prime factor to get my L mod k result. You'll see this in a moment. Okay. All right. So we use the strong form of the prime number theorem, integrate by parts the logarithmic integral of x, and then put that in. The calculation is a little bit involved, so I'm skipping the details. So you can actually show that m omega of x is equal to x over log squared x, and then some constant x over log cubed x, x to the log 4x, etc. And we get this representation for m omega of x. Now, at this point, we also, next we consider replacing this with the fractional part of x over n to use access theorem. So this is a traditional trick that we use in prime number theory. So using that earlier result, we can actually show that this is of this order of magnitude. When I first wrote this paper with my student, and I said I'm using access theorem arguments, the referee, while accepting the paper, said, access theorem only works for bounded functions, so you cannot apply it on mu of n omega n. So I actually did not say access theorem. I said the arguments underlying access theorem. So the Jeff Lagarius, who was the editor handling my paper, he wrote and said, Krishna, just formulate a more general version of access theorem, which works for functions which are not necessarily bounded, and then this issue will be resolved. So here is a version of access theorem where the functions need not be bounded. So if a of x is summation a of n is little o of x, so less than x eta of x, and eta of x, x eta of x is an increasing function, and suppose that the absolute value, sum, is less than x beta x is an increasing function such that beta x eta x goes to 0, then the sum a of n fractional x over n is less than x times square root eta x beta x, and this is the slightly more general version of access theorem than what you find in Hardy's divergence series. Okay, so we just use this. And then since we have put the fractional part, we now put the integral part. And now the integral part, we just use this identity, which I've called number 25. And therefore, that just turns out to be the negative of x over log x. And now we add the 2 to get x times mu of n omega n and divide that. And then you get that series equal to 0. So I communicated this to Pomerantz and, to Tenenbaum, and talked to him on the phone, and Tenenbaum said, I don't really know of people who have really looked at mu of n omega n combination, but you can do this using the Selberg-Delange method. At that time, I didn't tell him about the duality. I just wanted to know what the state of affairs was. So I'm now going to just give you a little sketch of how to think of this from an analytic point of view. All right. There's this famous paper of Selberg, published in 1954, in connection with the problem of Hardy on asymptotically determining the number of integers with a prescribed number of prime factors, k, but k can vary with x. Okay. So this problem was actually solved by a very complicated inductive process by the Indian mathematician Sathe. And it's an interesting story. Many of you may know this, but some of you may not. So Sathe submitted this paper to the Indian Journal, and the editor Chandrasekharan sent it to Selberg for refereeing. So Selberg looked at this paper and said, the results of Sathe are very beautiful, and it's very impressive that he has done this by induction. But really, a much easier and better way would be to do it analytically using contour integrals and using this generating function. And so Sathe had like 150 pages, and Selberg, of course, Selberg is very brief in what he writes, gave a 5-page derivation of Sathe's results in slightly stronger form. So Chandrasekharan felt that this was such an important referee's report that it ought to be published actually as a paper. So the referee must reveal his identity. And so Selberg's paper and Sathe's paper appeared next to each other in the Indian Journal in 1954. And of course, Selberg's paper has been very influential. So Selberg looks at this zeta s to the power of z, and we call this the generalized divisor function, the Dirichlet coefficient. And his result is that summation dz of n is x log x to the z minus 1 over gamma z with this error term z minus 2, and it's uniform in a circle of radius r. Okay, so what this means is that you can actually apply this method, and Selberg, of course, states that in his paper, to functions, Dirichlet series of the form zeta s to the z times h of s, where let us say h of s is analytic in real part s bigger than half. So in our case, we are going to look at s minus z of x, which is summation, I'm going to call it s minus z. I put a Mobius function here. And this actually has a generating function, which is written in equation 31 there. And we can rewrite it in terms of the Riemann zeta function by writing it as zeta s to the minus z times a g function. And now that g function has this product, and this is, of course, analytic in real part s bigger than half. So basically, Selberg's result gives s minus z to be that x log x to the now minus z minus 1 over gamma minus z g1 of z times this error term. Now, subsequently, Dulonge extended Selberg's method by saying that we can deal not only with zeta s to the z, but we can actually deal with log zeta s to an integral power k for those Dirichlet series having that as a generating function. It's not surprising that we can do that because zeta s to the z is e to the z log zeta s. So Selberg is anyway dealing with a branch point at z equal to 1 due to log zeta s, and he was using a Hankel contour. So once you are able to use that Hankel contour, you can deal with a product which is log zeta s to the power k. You can use the same Hankel contour. So I'm not saying Dulonge's result is not important. It's important, but it's not surprising that you can do it. But then he went through the details and established an asymptotic result, and that is known as the Selberg-Dulonge result. And this method is called the Selberg-Dulonge method. And Tenenbaum's book on analytic number theory, probabilistic analytic number theory, has a full description of the Selberg-Dulonge method. Now let me connect it with my m omega of x. I'm going to do a little heuristic here. So first, think of m omega x as the derivative of s minus z of x. Recall s minus z is mu of n times z to the omega n. So if you take d dz, the omega n comes down, and then you put z equal to 1, you get summation mu n omega n. So you think of it in terms of the derivative. But now take the main term that you get from the Selberg method and heuristically just take the derivative with respect to z and apply z equal to 1 just to get an idea of how big it ought to be. Okay, and when you do that, because of the fact that this function has a simple pole, you can easily calculate from that m omega of x must be of the asymptotic size x over log squared x. So that's what you saw in that earlier theorem. But of course, it turns out that C2 is 1. Now, all this can be established rigorously by the Selberg-DeLonge method, but I've just given here some details about the Dirichlet series that you end up getting. Now, as I told you, I wrote to Tenenbaum, and I also had a Zoom call with him. So he wrote back after I mentioned these results that you actually can get this series representation using the Selberg-DeLonge method. So that is equation 42 that he wrote to me. And then from there, he says that, of course, it follows by partial summation that the series mu and omega n over n converges. And then he does a little analysis there to show that that limit is 0, and therefore concludes that this series converges at least at this rate, and of course gets a series representation. Now, I want to point out a key difference between m omega x and little m of m of x of Landau. Maybe I'll just use the board here. The function m of x, sorry. Board is here. Okay, sorry. So the function m of x of Landau, that changes sign infinitely often. The m omega x is of size, m omega of x is of size x squared over x over log squared x. So obviously, it's not changing sign infinitely often. Right? So it turns out that this integral is actually 0. So this function m omega of x does change sign, except it doesn't change sign infinitely often like m of x. So m of x divided by x squared dx is also 0, as is this integral from 1 to infinity. Okay, so there is a change in sign, but it's at most finite number. Okay, all right. So there are key differences between the two series. Okay, so now let's come to I mentioned some of the bounds for psi of x, y. Of course, sharper results are known in terms of the Dickmann function. Now, with regard to the second largest prime factor, one little technical point, there are two ways to define the second largest prime factor. You take an integer n, you factor out the largest prime factor, and then you say the second largest prime factor is the largest prime factor of n divided by p1 of n. So in that case, p1 of n can repeat. So p1 of n can also be the second largest prime factor in this definition. Or you can define the second largest prime factor to be strictly smaller than the largest prime factor. So the two definitions differ only in a very small set. So here is a little theorem. The number of integers n up to x for which the largest prime factor repeats is of the order of magnitude no bigger than x over e to some constant square root log x log x. So we don't have to worry about which definition we use, but we're going to use the definition that the second largest prime factor is strictly less than the largest prime. Okay. So anyway, there's a little proof of that. So now the next thing is, and this probably addresses your question, how large is the second largest prime factor in general? So I did not know about this paper of Pomerantz, so I just started proving it myself. So in this particular case, we proved something like the number of integers up to x for which the second largest prime factor is less than e to the root log x is less than x over square root log x. And we can actually prove something stronger, that the number of integers up to x for which the second largest prime factor is less than or equal to t is of no more than the order of magnitude x log t over log x. Okay, so what you saw earlier on when you put t equal to 2 is that x over log x I wrote, and then you have this. And Tenenbaum actually has a paper on the case largest prime factor in which, as a special case, this result follows, but he actually has it in an asymptotic form. All right, so now, so I'm going to skip the proof of this. So this is my proof of that result. And that's Tenenbaum. All right, so now comes the main theorem from which the Mobius result follows. So just as we proved in 1977 that the sequence of largest prime factors is uniformly distributed modulo k, we now want to prove that the sequence of second largest prime factors is uniformly distributed in the reduced residue classes modulo k. Now, this is a little bit harder because the decay of psi 2 is not as strong as the decay of psi 1 to keep control of the error terms. So this is the theorem where you count the integers up to x, where the second largest prime factor is L mod k, and then you get x over phi of k plus this error term. So how do we prove this? So the first thing is we want to look at integers which have at least 2 prime factors. So the integers with 1 prime factor are the prime powers, and that's of the order of magnitude x over log x. So that's little o of x. So when you look at, so what we do is we classify the integers up to, so there's a little trick here. We classify the integers up to x in terms of their second largest prime factor. So S2 of xp will be the number of integers up to x with a prescribed second largest prime factor p. So if I sum that up to p less than or equal to square root of x, I should get all the integers up to x, which is x, except for the prime powers, and that's that x over log x that I have subtracted with x over log square x. So this is, first of all, an identity. Now, the next thing we do is we take an integer with second largest prime factor p fixed. So we can write it as mpq, where q now is the largest prime factor, and now m is an integer, all of whose prime factors are less than or equal to p. So that is where the psi function, the original psi function, comes into this problem. Even though we are looking at the second largest prime factor, it's influenced by the psi 1 function. Okay, so for various reasons, I broke it up into these 2 sums. I'm not getting into the technical aspect, but the main point is I write this summation. Keep in mind that that sum is of the order of magnitude of x with an error term x over log x. Is written completely now in terms of the Dickmann-de Bruijn psi function. Okay, so now this sum that I have written here, which I've broken up into 2 sums, is actually of the size of x. So that's very important. Now the next thing we do is we use the prime number theorem to convert the inner sum in both cases to an integral. Okay, so we replace it with this integral that I've written here. I call that original sum sigma, and I call this sum I, even though this is not a full integral, this is some of these things. But the key point is you can compute the difference between those 2 by using the strong form of the prime number theorem. But to use the strong form of the prime number theorem, you need to really have the variable go to infinity, because otherwise your e to the root log at the bottom has no role. You don't use the prime number theorem for x equal to 100. You have to use it for large values of x. So that's why I'm putting this lower bound y. But I got to choose this y optimally, because y, if the quantity primes less than y will count the integers for which the second largest prime factor is less than y, and we need to control that. Okay. So we look at this sum, and here is an estimate on the error here that I have written down, because I put 2 sums, I have that. So we end up actually showing that the integral is x plus x log y over log x plus a quantity which is involves e to the root log y, and the optimal choice is y equal to e to the 2 log x squared, and we therefore conclude that the term involving the integral is of the size of x. Now this is very crucial and an important trick, because I now want to show that the second largest prime factor is uniformly distributed modulo k. So I really want to show that that sum is asymptotic to x over p of k. So what we do is we take that sum and we write it once again in terms of the psi function, like we did before. But notice that when you write it in terms of the psi function, it is only in the inner sum that the L mod k condition comes, which means previously I had used the prime number theorem to rewrite that in terms of the integral. Now I use the prime number theorem for arithmetic progressions to rewrite that inner sum in terms of an integral. But the beauty is, in an integral, you can just put 1 over phi of k. In a sum, you can't just simply say, I'm now summing over primes less than or equal, which are in the residue class L mod k, and therefore it is 1 over k of the previous sum. You just can't say that. But if you replace it with an integral, in the integral, the 1 over phi of k just comes in naturally, and therefore we end up showing that this IKL is exactly the old I integral divided by phi of k, and the theorem on the uniform distribution follows. Okay, but it involves this little trick. All right, so once you have this theorem on uniform distribution, the next thing you do is you look at the Mobius function omega n congruent, smallest prime factor congruent to L mod k, and you show that this is little o of x. And the proof, of course, involves choice of the characteristic function, rewrite the whole thing, and you break it up into two sums. This sum is small o of x is well known, but now here we use the uniform distribution of the second largest prime factor. Okay, and that's uniform distribution tells me that inner sum is asymptotic to x over m 1 over phi of k, but then mu of m over m goes to 0, and that is how you end up getting this little o of x out of this. Now comes a very interesting cancellation. So Axel's theorem argument gives me that. Now we go to the integral part. Okay, so when you go to the integral part, which is the next one, very interesting cancellation comes. The duality identity involves omega n minus 1. It doesn't involve just omega n. So what you do is you separate it into two sums. One is just omega n and the other is the minus 1 part. The minus 1 part is my very first duality without omega. So that gives you f of the largest prime factor, which I already know is x over phi of k, but it has a minus sign. This other one, which is the sum of the second largest prime factor, has x over phi of k with a plus sign. So the two cancel. And that is the reason why summation mu of n omega n in this arithmetic progression, phi of n L mod k, is little o of x, because of this cancellation between what happens in these two terms. So this remarkable cancellation, and this is going to be even more interesting when you go to higher dualities. So anyway, you add all this up and you end up proving our main result. So this is the slicing result for mu of n omega n. Now, I'm not going to deal with exceptional primes because I want to keep track of time and finish on time. All right. Now let me make a couple of comments here. The way we approached the problem back in 77, and that's important to explain Dossie's work. So I looked at a function mf of x, which is summation mu of n f of p of n is little o of x. And I first proved that this is always little o of x. Axel's theorem gives this. And then the duality and the integral part gives me what I have here on equation 106. So when I add all this up, I end up getting x times mu of n is this equal to minus f of the largest prime factor of little o of x. And that is how I got this equivalence result. Now, at that time, I published this with a very weak error term, and subsequently, I was able to determine the precise order of magnitude of this uniformly for all f. Okay. Now, the analogous approach here would be to do mu of n omega n f of the smallest prime factor of n. And I'm working on this with another of my PhD student, Yazan Alamoudi, who is from Saudi Arabia, very brilliant guy. So this paper is under preparation. But now I want to explain what is actually going on. So you look at omega n minus 1 f of the smallest prime factor of n with integral part. That gives you f of the second largest prime factor. So when you separate out the omega n and this, the result that you actually get is summation mu n omega n f of the smallest prime factor of n over n, this sum, is equal to sum of f over the second largest prime factor minus sum of f over the largest prime factor. So the theorem that we have for general f is the following. If f is a bounded function on the primes such that the average of f on the largest prime factor and the average of f on the smallest second largest prime factor are the same, then this sum is 0. So what we are proving in our previous case was we took f to be the characteristic function of primes in an arithmetic progression. And there I had the prime number theorem for arithmetic progression as my tool. And that showed that both of these values, kappa is 1 over phi of k. That's the cancellation that gives 0, which means the theorem that you can formulate now is if this has one average kappa 1 and this has another average kappa 2, then this Mobius series will be kappa 2 minus kappa 1 is what you will have. So I now raise this as a problem. Probably I should give this in the problem session. Does there actually exist a function on the primes which has two different averages, one on the largest prime factor and one on the second largest prime factor? My conjecture is no. If you assume that f has an average on the primes, that average will be the same on the largest prime factor and second largest prime. So the question is, can you find some sort of a function where the average is fluctuating, upper and lower density, but then for whatever reason, the largest and the second largest things adjust themselves? I do not know. I have not been able to prove any theorem of this type. So this is an interesting problem to consider. Now, after seeing all this work, Pomeranz proved the general result that if P is a set of primes which has a density in this sense, that summation log P less than or equal to T, P belonging to T divided by 1 over T minus kappa is little over 1, then this series, mu of n omega n over n, where the smallest prime factor belongs to P, is 0. So my point is, this is a very nice result, a very general result. But I think our result, which gives the connection between the largest and the second largest, shows intrinsically how you get the 0. You get the 0 due to a cancellation. So he is able to get the 0 without appealing to a cancellation. But he is assuming that this function has a density on the primes. But if you have a density on the primes, that density will be the same on the largest and the second largest prime factor, and therefore the cancellation will take place. So there is a relationship between our two results. Now let me explain the generalization to algebraic number theory. So this is due to Darcy. So she considers a finite Galois extension of Q with Galois group G and takes a conjugacy class C. And then she counts mu of n over n, n bigger than or equal to 2, such that this Artin symbol, K over Q with smallest prime factor of n, is equal to C in this conjugacy class. And then she proves that this sum is minus of the size of the conjugacy class divided by the size of the group. What does this mean? If you take K to be a cyclotomic extension of Q, that has got order of magnitude phi of K. It's abelian, and therefore the conjugacy classes have size 1, which means this is 1 over phi of K. So her point is that the results I proved come out as a consequence from this in the case of a cyclotomic extension. Of course, she relies on the strong form of the Shebatov density theorem due to Lagarius and Odlyzko. But now the point is this: how does he actually prove this? The way she proves this is she counts the number of integers up to x for which the Artin symbol with respect to the largest prime factor is asymptotic to this. So what does that mean? This is the constant little c that I stated in my first theorem for the average of the largest prime factor. So once you prove that, my theorem says that if the function has an average on the largest prime factor, then the Mobius series will converge to minus c, which is really what she is proving here. Okay, so it is really that same idea, but now applied to the number field situation. Okay, now finally, so here are some statements about others who have extended this. So instead of Galois extensions of Q, this result of Darcy has been generalized by others to algebraic extensions of a general field. And again, all of this relies on the Shebatov density theorem. Now, here is the result where the Ramanujan sum has replaced the Mobius function. Ramanujan sum, of course, is a generalization of the Mobius function. And now I want to say something about the work of my student Sengupta. So Sengupta did the following. Just as Darcy extended my original duality result, which is the case, I'll say first order duality, to Galois extensions of Q. Sengupta was successfully able to extend the mu and omega n results that I had to Galois extensions of Q. So that paper appeared, I think, last year in Research in Number Theory. Okay. Now, we are now working on higher order duality. So let me just conclude with that. So analogous to that, we prove here that summation mu of n omega n to the k is little o of x. Actually, it's a very interesting series. This series has x over log squared, and this is a polynomial in log x of degree less than or equal to k minus 1. You can determine this polynomial, and then the next one will be smaller things with log cubed and so on, but the polynomials change. And of course, you can use this to prove a result of this type, and here also you have an expansion. But I want to say something about, and of course, the key thing relies on the kth largest prime factor being uniformly distributed modulo L. But now what I want to mention here is, how does the cancellation take place? So there it was largest minus second largest. When you get to the kth largest, how does the cancellation take place? Well, we take x to the k minus 1, and we write it in terms of factorials, right? X minus 1, x minus 2, x minus j plus 1, and sum, and you get Stirling numbers of the second kind, which I've given the recurrence for the Stirling numbers of the second kind. Now, there is an interesting cancellation for Stirling numbers of the second kind, and that is written here in the lemma. I searched the literature. I couldn't find this particular cancellation stated anywhere. I mean, I went into various things and all sorts of properties of Stirling numbers. But maybe I'm not so good in searching, but nevertheless, I couldn't find it. So we just proved this lemma. So what happens in the case k equal to 3? How does the cancellation happen? Very interesting. When you work this out for k equal to 3, you end up with minus of f of the largest prime factor, this identity, 3 times f of the second largest prime factor, minus 2 times the third largest prime factor, and that is 0. So the cancellation is quite striking. It's a combination between. So in order to study this problem at level k, you need to know all the results up to level k minus 1. See, for example, so the second largest prime factor result I had relied on the largest prime factor. So the third largest for this duality will rely on both the first and the second, and so on. So this cancellation is what essentially is dominating this and is leading to this result for it. Okay. I think there are people working on extending the higher order dualities to algebraic number fields, but there are also maybe other generalizations that may come out. And I think this is a particularly nice problem for young people, graduate students, and so on, because there's a lot going on here. You can do it both analytically as well as elementarily. So I just wanted to share this with you. Thank you. Oh, let me just give you the references. Okay.
Yeah, thank you again.
You're true.
And the next talk will be in 10 minutes.
So when you ejected, we have a question here. One second. When you ejected, can you make sure it is safe to eject?
No,
You just pull it out.
I just pulled out.
It's
If- Well, sorry, I didn't say that. I said I just pulled out.
yeah.
If you know a better way,
No, the first thing is how do you supposed to move this?
can you get in here?
Somewhere it should say.
Wait, I have to do one of that. Wait, 1 second.
You put it on.